Welcome back, everyone, to the Python tutorial seminar series. Thank you for your patience over this little break we had over October. Today, Anissa Zacharias will be covering advanced plotting techniques. And thank you to anyone who submitted their visualization requests. Anissa will not be able to cover them all, but there'll be more plotting tutorials to come in the future. Some basic understanding of matplotlib and NumPy is expected to get the most out of this session. Before we begin, I need to review our code of conduct. By joining this Zoom call and participating in this tutorial seminar series, you've agreed to adopt these values and engage in respectful communication only. Any inappropriate remarks in the chat will have you removed from the call by one of our co-hosts. The seminar is only an hour long, so we cannot stop the lecture to give individualized attention, but there'll be a number of co-hosts in the chat able to answer some calls, and otherwise we'll be able to get you up to speed with individualized one-on-one attention afterwards. So if technical issues arise, please sit back, relax, it's only an hour, and we'll do our best. Your speaker today is Anissa Zacharias. She's a software engineer here at NCAR. She's a member of the GeoCat team working on computational and visualization tools for geoscience applications. She has an MS in computer science from Georgia Tech and a BS in computational mathematics from Embry-Riddle Aeronautical University. So she is very qualified to help you with your visualization techniques today. And here are some learning resources for today. Stack Overflow, as always, today's content on a GitHub repository that I will post in a second. A little type of plot cheat sheet, and some tips for making custom color maps. More of these resources will be shared by Anissa throughout the chat or throughout the seminar. And with that, I'll hand it off to her. You can take it away, Anissa.
All right, hi. Let's see if I can get the screen share going. All right, I'm assuming that's working. This is the second matplotlib tutorial, second and a half. The first one covered the basics, and this will build off of it. And there was also a tiny matplotlib plotting section in the plotting with GeoCat Viz tutorial that you don't need for this tutorial, but both are useful. Here is the repository. This is the same as the first one. It has changed a lot. If you want to go back and rewatch the first one, you can go ahead and look at over here for the releases. There is an archive of how exactly this repository was for the first part. And I would recommend that you completely reclone this for this one. It has changed a bunch. There is a new environment that we're going to do. But you can also do a git pull if you really want to. All right, so I'm going to go ahead and clone this fresh. I'm going to be putting this on my desktop. And now I'm going to go into the folder, matplotlib tutorial. Also, this installation instructions is on the bottom of the GitHub page. And you can also run this tutorial on Binder if you want, instead of doing all this locally. So once you're inside of the folder, we're going to make an environment, and we're going to do that with conda environment create, and then F for file, and then we're going to give it the environment file. This is a different environment than we used for the other two tutorials. I already have this environment locally, so mine won't generate, but yours should take a minute and get going. So now I'm going to do conda activate MPL and once we're inside and have our environment activated, we're going to launch Jupyter Lab. And if you're joining us on Binder, this is what we should have popped up already. All right, so we're going to start with annotations. If you go from here, which is the initial folder of the repository, you can either follow along by going into notebooks and going on the second and third notebook, or from here, you can follow in tutorial blanks, which are blank versions of this, which I'm going to be typing on. and kind of just following through the fully filled out versions that you can find in notebooks. Either way is totally fine. All right. So our learning objectives for this is annotations and labels. This was a highly requested topic. It's going to be a little short. There's so much stuff you can do with the annotations and labels, and this will just, it'll show you where to get started. So we're going to learn about annotations, and we're going to learn how to render math symbols in those annotations. So for our imports, we're going to do matplotlib and numpy as expected, and we're also going to import scipy real quick. This is only for the purpose of the setup and to get something that we can annotate onto. It is not actually a fundamental part of the annotations. So we're going to start off by setting up something to annotate on. I'm going to generate a normal distribution with that scipy package that I talked about, and then I'm going to annotate on top of it. So just some math really quick. I'm going to set up some variables to generate the normal distribution. I'm assuming my typing is going to get better throughout the tutorial. Sorry about that. So we've got a mu, a variance, and then a sigma, which is the square root of the variance. And now we're going to create some X data so that we can generate a normal distribution on top of this. So we're going to make a NumPy linspace. And the range we're going to be plotting this on, I'm actually going to define from the variables that I'm going to use to generate the normal distribution. I'm going to do it 3 sigmas out from the middle, just because if you want to change these, change the variables that we're using to generate this will have it automatically resize. Just totally optional. Sigma, mu minus sigma to mu plus 3 sigma. And we're going to give it 200 points over this range. And then we're going to get our normal distribution, which I'm going to put in a variable called PDF. And we're going to get this from the stats package, norm.pdf. And we give it the linspace that we're going to be plotting over, our mu value, and our sigma value. So what this is going to do is for each point in the linspace in X, it's going to give us a corresponding point on what a normal distribution would be on the mu and sigma. So it gives us a really clean, nice curve. And let's plot it just to see where we are. Nothing crazy setting up figures. I just want to see where we're starting. Plot X and PDF. All right, so as expected, a really nice normal distribution, not much to it. We're plotting, or we're, as a part of the output cell, we are having this right here. This can be muted by putting a semicolon after the last line. Stylistic choice, totally optional. For some of them, it might kind of be wonky if you print out everything, but your choice. And let's add some annotations to this. So I'm going to make a new cell down here below. And again, I'm just going to pull this call right here, the plot call, while in the variables in the notebook will propagate over like cell to cell. So for example, I still use mu, sigma, X, and PDF in the second cell, but to get the plot down here again, I'm just going to call the plot again. The plot won't carry over as nicely between cells. So, and for this, I'm going to add a plot.text, and this is going to be our annotation. Say you're doing something and you're teaching like a math class or I don't know, a matplotlib tutorial, and you really just want to have the equation of what we're plotting written out. This is going to involve a lot of math symbols, and there's not really a good clean way to do it that you can think about from something other than matplotlib. You just want to do it in matplotlib. And we're going to do that with plt.text, matplotlib pyplot.text. It's going to, I did just steal this from the completed notebook. Typing this out would be terrible and probably take me a couple attempts, but we'll go through it input by input. So the first input to plot.text is positional. This is on the plot right here, the bottom left position of where the text is going to start. And the second one is the Y. So the this text that I'm going to render right here is going to be generated the bottom left corner starting at -1, 0.05 on the coordinates that we're using to plot the data. This is the grid reference it uses by default. You can also specify a different grid reference. For example, if you're doing like polar, you can give it, I'm going to be giving you the X and Y coordinates in polar coordinates, or you can do it based on like points instead of the actual data points, the data values that you're going off of. But going based off the data values here is quick and easy and fine in this case. And then the third argument is the text that we actually want to put on the plot. And as I said, I wanted to do some like formula stuff. I wanted to have it look like LaTeX. And so how we do this is we do something called math text. There's a reference later of all the different ways you can do math text. But essentially what it is you have a string that you put an R in front of, which means a raw string, and you surround whatever math text you're going to be doing in $signs. And then if you're familiar with LaTeX, you just type out essentially what LaTeX would have it look like. It's not exact. It doesn't have all the fancy symbols that it has, and some things are slightly different, like the brackets that you put in front of like square roots. You don't have to do it all the time. Small differences. But it's essentially LaTeX. And so if we run this, we're gonna get a little equation on our plot right there. This isn't ideal, it's small. And from this equation, there's exponents, there's tiny little things. It's kind of hard to see. If you notice, if you zoom in on the actual web page, like I'm doing here, it doesn't actually get any better. That's because when matplotlib makes this, it rasterizes it. It turns it into literal, like little points, especially in JupyterLab. And so zooming in doesn't really help us here. So we're going to need to do something to make this a little bigger, a little cleaner. Additionally, if you do this, say you want to like print this won't work just like as a printing thing. For example, like I'm just going to pull this here. I'm going to make a new cell and I'm going to say print and then this math equation. That won't work. That's because this math text is exclusively something used by matplotlib renderer, and it's matplotlib that's actually forming the little equations. It's not something that Python will just nicely do for you. So let's take that away and let's do another iteration on this. So again, we're going to pull down the plot call and we're going to do some more fancy things. I'm going to pull out the string because I'm going to be putting more inputs into the text call. So I'm going to call this big old long chunk, I'm going to call it F string. And I'm going to put it right up there. Yep, same thing. Sorry. And so we have this plot call, we have an F string, and I'm going to add in the text again. So plt.text. And I'm going to actually, I think I want to center this. You can see that I've tried to center it. I've kind of ifed it. And so it kind of looks in the center, but I actually want this to be centered on 0 right here. If I want to go back and change this equation, the equation of a normal distribution, I really want it to stay centered on the 0. And so I'm going to give it an X position of 0 and the same Y position of 0.05. I'm going to give it the F string. And I'm going to give it a keyword argument of HA equals center, which is going to make this centered around 0. And I'm also going to increase the font size, which I can do with the keyword argument font size. And I'm going to just bump it up a little bit to 15. I think the default is like 11, somewhere between 10 and 12. And then I'm also going to do one more thing. I'm going to, in the plot call, I'm going to give this a label. You can generate this math text on any aspect of this right here. And while the text is labeling, I actually want to do a actual matplotlib label and legend. So in this plot call, let's do label. equals, and then another math string, or math text string. So again, the R and then the open quote marks and surrounding it in $signs. And I'm just going to give it the parameters of what I was using to generate it, which is mu equals 0. And then this means space, so 2 spaces. And then sigma squared equals 1. And now this is fine. If we run this, label doesn't actually show up. That's because to get the labels to show up, whenever we add a label to a plot object, and then the plot object is displayed on the matplotlib figure, we actually need to call plt.legend. We don't need to supply anything to plot.legend, although we can if we want to customize it. And what this will do is it will pull all the labels and it will put them nicely in a little legend up there. And as you can see, it's rendered nicely as well. And also our little F string is now bigger. It still might be a little small, but you can see where we're going there. It got a little bigger. But okay, so this is fine, but there's definitely more to labels. One of the most popular requests, apart from annotations, was somebody requested to have labeling of the x-axis with math text. So we're going to do a little extreme example that does that and some other customizations. Now, I don't know why you'd want to do this, but you can. That's the cell I deleted. All right. So we're going to do an extreme example. Again, we're going to call the plot. And we're going to do a generic curve. I'm going to take away these things. I'm going to replace the x-axis with kind of like, you'll see, with like symbols describing like what on the normal distribution it is. And I'm going to take away any identifying features. This is going to be, I'm not going to sub in values for like mu and sigma, basically. Let's pull the F string again. I guess I don't have to actually pull F string, but I'm going to, because that's the way it is in my example. The text call again, starting with 0, 0.5, F string, HA equals center, font size equals 15. And now I'm going to do some additional customizations on this. So when a plot.txt is created, it comes with something called a bounding box because it is an artist, if that makes sense. When you generate things in matplotlib, often you can edit them in the same way based on what kind of thing they are. For example, a lot of things are considered as artists and they all have their own bounding boxes, and you can edit the bounding box in the same way generally for everything. So I know how to access this. I'm going to give it the keyword bbox from here, which will access the text bounding box. And I give it inputs as a dictionary. And this is the same thing as saving text inputs here, but then our input has outputs, essentially. So I'm going to do bbox dictionary, and you can give it, for example, a box style. One of them is called sawtooth. There's also what's like, I think, round, left arrow, right arrow. You can have arrows pointing in both directions. There's a bunch of them. I can give it a face color equals yellow. You could give it any color. And then EC, which is edge color, equals red. And look at that. We've done something wrong. I missed a 0. Also, as you just saw, you can make labels outside of the plot. Outside of the, like this little, the axis box, you can make labels outside of it. That's what I meant to do though. All right, so again, I don't know why you'd want to do this, but you can. And let's go and add custom X tick mark labels. I'm sorry to the person who gave the NumPy tutorial, but I'm going to do this longhand way. We're going to define X ticks where we want our labels to be. I know where I want my labels to be, and it just happens to be the same as the plotted automatically. And I'm also going to define another one called X labels equals, and I'm going to copy and paste this. And I suggest to do the same because it's rather long. X labels equals, and you can see each one of these is a string designed to be generated with math text that is going to appear at these X tick spots. So the first one is going to appear at -3, the second one is going to appear at -2, and so on. And to get these to show, we do plt.xticks x ticks and give it first x ticks, the locations that we want our labels to be generated at, and then x label, the what we want to show up on those labels. And so if we do that, see, this is where you'd probably want to meet the output. Look at that. So we have kind of a generalized x-axis for this. Now, I also kind of want to remove the y values here because this is, I have the x-axis generic and I have this formula generic and I don't have the legend anymore. So I want to just quickly turn off the y ticks as well. We do that the same way as the x ticks, except for we don't have to supply it with anything because instead of x ticks and x labels, we're just turning them off. And there we have it. That's how you do a bunch of labels, customizations, texts, annotations, and math texts. Down here below, I thought I called the typos. There's a typo. All right. So here are a bunch of more resources. Here is the text documentation, annotation documentation, matplotlib's annotation examples, which is very useful and get into even weirder looking things than we've done here. This is how you do math text and math text examples and drawing fancy boxes, which shows you all the different ways that you can edit the little bounding box that I was talking about. All right, so the second topic, I think the most popular requested topic that we had was color bars, actually. Color bars, subplots, different plot types, and those are all covered here with an overarching topic, I guess, of color bars and color maps. So our objectives for this one are learning more about color bars, creating a plot with shared color bars, making custom color bars, and as a bonus, making 2D histograms. And also an additional bonus that I didn't put up there is doing fancy versions of subplots. All right. So for this one, we have the same starting inputs, and then after we do, imports, and then after we do that, we're going to do a bit of talking about kind of color map theory, an extremely abbreviated version, and anybody who actually does color maps will probably be aghast at this explanation. But I found this really useful when I was first learning about color maps and thinking about how I should be using them and on what type of data. So I'm just going to quickly go through it here. All of this, by the way, is pulled directly from a matplotlib page that I'm going to link both after the section and at the bottom of this if you want to go see a more scientific and well-explained version. So matplotlib has classes of color maps. The first one being sequential, which is a change in lightness and or saturation of color incrementally. And this is good for data that has ordering. And there's also several different classes of sequential color maps. The first one is perceptually uniform sequential color maps, and it's the color and or saturation. It changes uniformly as the color map proceeds. And then there's just basic sequential color maps, which start off from a desaturated version of the color and go to a saturated version of the color, but not quite as uniformly as the perceptually uniform ones. And then sequential 2 color maps. They don't have any sort of special names, but they don't necessarily have that same desaturated to saturated perfect stream. Also, some of them have different colors, but are still technically sequential. Things like that. And what's most interesting to me about this is actually something called a lightness variable, a calculation that MATLAB did not create, but they're using to evaluate this. And it's a kind of a perception of how light the color is. And they also include the lightness maps for all of the different color maps. And here they are. So as you can see, for the perceptually uniform ones, it's a very, very straight line. For every change in lightness, there is a corresponding change, like direct change in whatever data that you're using. For the sequential color maps, they're not quite as straight, they're a little wiggly, but they all go from a darker lightness to a higher lightness. Lower lightness? Yeah, lower lightness to a higher lightness. And the other ones, sequential 2 color maps, they're a little wiggly. They don't follow this nice pattern. Super nice, a little wiggly, but still following the same thing and kind of doing whatever they want. And this is important because say you're using something like this hot one right here. As you can see, it might change the way that the kind of the spread and the velocity, I guess, of your data is being perceived. That's why sometimes, if you're like trying out different color maps and you use different ones, it makes your data look really, really different. Not even just like different kinds of pretty, but it highlights like different aspects of the data, and you can use different sort of color maps for different sort of things. And anyway, I really think these lightness plots are cool and something to keep in mind while doing it. The second class of color map is diverging, which is a change in lightness and or saturation of 2 different colors that meet in the middle at an unsaturated color. This is important for 2 different colors. If they were the same color, it would actually be a cyclic color map, which we're going to cover next, and should be used when the data has a natural 0 point, such as sea level, which makes sense. Like if you have data and like below the sea and above the sea, anything that just has something where a 0, which is not necessarily where you have like a diverging point that is contextually important for the data. And here are the lightness maps for these up here. They're just cool. So the next one, as I mentioned, cyclic color maps, which is a change in lightness of 2 different colors that meet in the middle and both begin and end at an unsaturated color. This should be used for values that naturally wrap around. The example the matplot gave was, I think, like calendar data, which I guess would make sense. And here are the lightness values for these. And specifically, I wanted to point out this HSV color map, which is has a really wild lightness map, and we're going to come back to this later. And the last class of color maps that matplotlib has is qualitative color maps, and these are kind of just miscellaneous. And it should not be used for data that has ordering or relationships according to matplotlib. I don't know of what pastel ones are used for, but yeah, these look kind of wild. Here are also miscellaneous color maps, qualitative and miscellaneous. So prism, flag, ocean. I think the most common one here is maybe terrain or earth, or I don't know, I've seen some people use just rainbow and jet. Each their own, I guess. And here are the lightness maps for these. They're super wiggly. The ones with like distinct colors, they look wild. All right. And so other considerations when you're going to be choosing a color map, 2 main things is colorblind friendly patterns. GeoCat has a whole section on this, on picking better color maps, which can be found at that link there. In general, if you just avoid color maps that have both red and green in them, it can mostly avoid this. And the second consideration is grayscale conversion. I don't know about you, but in college, I generally had professors that would print out things that were meant to be like in rainbow or something. And when they printed it out, the color maps looked silly and they didn't make any sense. And so coming back to this HSV one, if we print out this HSV as suggested by the lightness plot, it doesn't make sense anymore. This doesn't look like a progression. In rainbow, it makes sense. It follows a rainbow. But as soon as it's converted to black and white, you wouldn't be able to tell what is what. You wouldn't be able to tell any sort of cycle in what direction the data was heading, nothing. So definitely these are things to consider when choosing color maps. Here's the link I was talking about choosing better color maps. And there it is again, down there. And before we actually go to the typing part of this tutorial, I do actually want to point out this plot types cheat sheet. I wasn't sure what to call it. Plot types cheat sheet seems appropriate, but this is what it is. I think I just, nope, okay, still there. And so this was in request. A lot of the requests that we got were for things that are on this cheat sheet, this is my favorite matplotlib cheat sheet ever. It goes over the different colors. This is the anatomy of a figure from last time. It goes over all the different plot sizes and the inputs you're going to need. It's on Google Drive. It downloads as a PNG. I don't know. It's still my favorite. It goes over some projections, line styles. It even does some, oh dear, zooming's not working. Some colors, some tick locators. Yeah, there we go. Gives you matplotlib color names, annotations, styles, labels, even some of the color maps we just talked about, legend placement, text format, so much stuff. So this is a really great resource. All right. And so now we're actually going to do some typing. So this was covered in the first tutorial, but since this is all about color bars, we're going to make a basic color bar again. For this, we are going to be using another normal distribution, except for this time we're going to be using NumPy's random normal, and we're going to be making a histogram as a kind of bonus. We're going to be making a two-dimensional histogram, and we're going to generate points with a normal distribution and then use hist2d to generate that histogram. So I'm going to make random distributions of 1,000 points. And I'm going to have them be binned initially into 15 bins. 15 bins. And now I'm going to define some data. I'm going to have x equals numpy dot random dot normal and give it size equals number of points and pt. Yes. And then the same thing for y. This will look different for all of you because I'm not setting a seed here for the random number generator to perform like consistently across things. That'll look different every time you're in the notebook. Yeah, so there we go. We've generated some data. And now we're going to plot this. I am actually going to do a fully blown out figure and axes. And then I'm just going to grab the axes with plt.gca, which stands for get current axes that were just generated by the figure up there. And now to generate the histogram, I'm going to do plt.hist2d, which is how we make histograms. And then the inputs to this are our X and Y data, the number of bins, and a keyword that you don't have to use, but I enjoy using, especially for non-2D histograms, like 1D histograms, is density equals, and we're just going to set that to be true. By default, it's false. This is actually like if you think of a 2D histogram, it will put the y-axis in terms of probabilities instead of bin count, which is, I don't know, I prefer it. Totally up to you. And then the most basic, simple way to add a color bar is you do plt.color bar. Don't even have to give it anything. And look at that, there we go. So this is our 2D histogram. Yours might look different. It's totally fine. As long as it looks something like this, you've done it right. And so yeah, we've created the most basic color bar, and it's only gonna get more complicated from here. The next thing we're gonna do is we're gonna make a shared color bar across two subplots. So to do that, we're gonna make our figure and axes with plt.subplots, which is also something that was covered in the first tutorial. And so I know that I want two subplots side by side. And so I'm going to do n rows equals 1 row of plots and n calls equals 2. I want 2 plots on the 1 row. And I'm also going to set constrained layout equals true. And this is just a nice keyword. It kind of keeps everything compact. This is the same thing, pretty much as calling, actually, I don't know if it's the same exact thing. I think it is, as calling plt.tight layout right before you do a plot. It's just something nice to keep everything all compact, and it does like the padding between the plots. It just tries to figure out like the best optimization for everything to go essentially. And I'm going to define two histograms. I'm actually going to save them out to instances in here for the purposes of making the color bar later. As you saw before, you don't have to save them out for it to be plottable, but I'm going to save them here. So hist1, and I'm going to plot on the first axes, which I'm going to get with axes 0. If we do axes, you can see that it plots them, but it's an array with 2 axes subplots in them. So to plot on an axes, we have to subset to a singular set of axes, axes 0. So again, hist1 equals axes 0 dot hist2d. Again, x, y, bins equals 15. Density equals true. And that's it for now. All right, so, and then we're gonna do it again. And the thing I'm gonna change between these subplots as to not drag this tutorial down with a bunch of like data generation is I'm just going to change how they are binned. Again, these aren't exactly functional plots that you'd want to create, but the purpose is to look at the color bars, not to critique my histogram making skills, please. All right, so we're gonna plot this on the first one, and we're gonna make a shared color bar. Actually, can we just see what that looks like? Yeah, so same data, just binned differently. And so now we're gonna define a color bar. And we're going to do this by referencing the fig.colorbar instead of just calling color bar from PLT. Color bar. And how we make this shared one is we give it fig.colorbar, and then we give it the plot that we want to base the color map on, the color bar on, where we're pulling it from, and the axes we want it to spread across, and then some positional arguments, or keyword arguments. All right, so the first one, we're going to give it hist. Oh, that one's going to want to be a 2, isn't it? All right, hist1. I want it to spread over all of the axes. This is actually, you give it a list input. We're going to do this more later, so you'll get a hang of it better. But I know that this axis right here, as I just showed you before, is a list of all the axes that we want this color bar to spread. So I'm just going to give it that. And then I want it to be on the bottom. It, by default, I think plots on the left, but I want it on the bottom. And we're going to run that, and it's going to break. All right, so this is because of what hist1 actually is. This would work better if you were doing something like a contour, but for what you want to put in here, what you want to put in here is the plot object. It's before, when I was like muting the output of the normal distribution, it was the first thing that plotted out the matplotlib object. But what hist2d is actually outputting is not just that matplotlib object, but the arrays of what I used to calculate the histogram. We didn't give hist2d a histogram. We gave it 2 one-dimensional arrays from which it formed a histogram. So what we actually want to do here is subset hist1. We can mute this for a second, and I can show you what hist1 actually looks like though. So this is what hist1 looks like. It's actually a tuple. It has arrays, 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 and then look at that, a quad mesh. That's the thing we want to be giving color bar, is this quad mesh. So if you didn't know that, which I didn't when I was first doing this color bar, that's how you would find out. You want to plot it on the matplotlib object that this spits out here. And because I've done this already, I know that it's in the 4th position, the 3rd index. And look at that. We've created something nice. However, there is a but here. So you notice I said that we give it the matplotlib object that we want it to base the color bar off of, and then we spread it over axes. This isn't a shared color bar. It's a single color bar plotted across axes. So for instance, this is the same data. So this is fine. Actually, the binning might make it slightly different. I'm not sure. But it might not be accurate to both subplots, if that makes sense. So to combat this, there are several ways of doing it. I know that both of them start off at 0. They both have to start off at 0 because it's a 2D histogram. But what we don't know for sure is the maximum that we want. So from up here, I can see that the maximum is going to be around 0.15. Yours might be different. What matters is that no matter what the top is, that they share a range, essentially. So for this, I'm going to just give it the histogram, a secondary keyword argument of v max equals 0.18. And again, down here. And look at that. It did change a little bit. So now this is an accurate shared color bar. The color bar beneath both of these plots is accurately representing the color bar used to generate these plots. All right. So the next thing we're going to do is custom color bars. And so I showed you before up here all the different options that you could do, but say none of these are doing it for you. You want something else. You want to be able to define your own color bar. So I'm going to show you how to do that now. We're going to pull additional things in from matplotlib. From matplotlib colors, we're going to import, normalize, and listed color map, and I'll show you what those are for in a second. And now we're going to choose some colors. From that cheat sheet that I showed you before, you can choose any of the listed colors, or you can make colors in other ways, just some colors. I'm going to choose some listed ones. Excuse me. And so I've already done this, so I know what mine are going to be. It's just going to be a bunch of them. This isn't going to be a pretty color map, but it's going to be an educational one. So those are the colors: white, pink, red, orange, green, blue, purple, and black. Not going to make much sense. The color bar theories from the first section are even matter now. And now to make these into a color bar, what we're going to do is CC map is just where I'm going to put it for custom color map. And I'm going to use listed color map. And I'm going to give it this list of colors to make a listed color map. And I'm also going to make a norm, which takes the place of this kind of manual v-maxing that I was doing above. So when I make a norm, this is something that I will feed into the histograms to make sure that they're both kind of plotting on a normalized range. So I'm going to give it vmin equals 0 and vmax equals 0.18, which is what I was doing before. All right, cool. Now I'm going to do figure axes to make the same thing equals, I'm just gonna pull it. Yeah, there we go. This is again copy and pasted from the completed one. This is just a lot of typing, and you guys aren't here to watch me type. So there we go. This is the same thing, the figure and axes, except for when I get down to the histograms, histogram 1 and histogram 2, I'm giving CMAP equals custom CMAP and norm equals norm for both of them. And again, I'm going to do CBar. Fig dot color bar. Again, I'm just going to give it hist1 and the third index. Ax equals ax, the list that we know spreads both of them we want. And again, location equals bottom. And let's see what that looks like. A mess, but it is a custom color bar. We did it. So it starts white, pink, red, orange, yellow, green, blue, purple, and black. Not a functional color bar, but that's how you make custom listed color bars. But this is it's segmented. It has it's the list of colors broken up, which I guess is exactly what it was supposed to be. But say you wanted a nice smooth one, like this one, I think it's Viridis, and you wanted something that nicely transitions between colors instead of having it be so choppy. We can do that too. So to do this, we're going to use from matplotlib colors, we're going to import linear segmented color map. And this works in much the same way. We're going to call this one custom blended, that's what it was, custom blended color map, CBC map, and then linear segmented and then we're going to give it from list. And the inputs to this are a name. I'm just going to do the same thing, CBC map, and the same list of colors that we had up here. And then we're going to do the same thing, which I'm pulling for the sake of time. And look at that. Now I have a nice blended color map. And so I know we're running short on time, but there is this last little section here, which is the challenge section. And this is, I've never had to do this in color bar. I've never had to do most of this, but just so you know, all the range of stuff you can do with color bars, we're going to go through a mini master's class of the hardest thing I could think of to do. All right, so what we're going to do is we're going to create subplots, multiple subplots with multiple different spanning ones with a custom color map that has a weighted color bar that has different segments taken out of it. All right, we can do this. Okay, so this is going to be a lot of copy and pasting, so I don't have to type this out so I can get it in time because I think it's really cool. We're going to make some new colors. I looked at these colors before. I pulled some with pretty names from the colors, listed colors in matplotlib. And then what I'm defining here is nodes. And so you can have the different colors start and end at different places. The most important thing is that one, you have the same number as colors as nodes. The first one is 0 and the second one is 1. So dark magenta is going to start at 0, light steel blue is going to start at 0.2, and honeydew is going to end at 1. And we're going to do the same thing, pretty C map, linear segmented color map. And then to get that in there, we do list and zip the nodes and colors together. And in Jupyter Notebooks, you can actually preview your color maps by just outputting it like this. The under value is for anything that is like below vmin. Bad is like for like NaN values, and over is anything that's like over Vmax. We didn't define any of those, so these are the defaults. So that's pretty cool. But I told you that we were gonna do like chunks, that we were gonna do chunks of different colors. And so that's what we're gonna do now. So to do this, what a color map is actually a color lookup table. And so if we get that color lookup table and we change values in the table and define it as a new color map, we can do so many things. We could subset a backwards color map inside of a different color map. If you choose values that are outside, like, or in between points, I'm pretty sure it does a nearest neighbor lookup. Yeah, it does a nearest neighbor lookup and just chooses a color. All right, so we're gonna do something called alt colors. And here we are. This is the pretty C map. And then we're going to get out a 265 colors out of it. And this is the lin space. And it's an array. This is the array of colors. This is the RGB values. And then the last one is an alpha value. So this is the array values of all the values, all 256 values that are making this. And I'm going to take a chunk out of it and make it green. And I'm going to take another chunk out of it and make it pink. Like you could do the same if you wanted to highlight like values in this one, or like specifically what you're looking for, or I don't know why, but you can. So these are the values for pink and green in an NumPy array. And then I'm going to put them into alt colors like this. I'm going to take a slice and I'm going to assign it to green. So this is going to take all values between 110 and 140 and put them as this green, and all values between 200 and 230 and put it as this pink. And now I'm going to change it back into an actual color map instead of a list of colors. And I'm going to do this, and I'm going to call it alt pretty C map. And I'm going to do a listed color map because this time it is a list of colors, just instead of a list of actual colors, it's a list of the values of colors. And then I'm giving it the alt colors that we just made with the pink and green. And we're going to show it out again. And look at that. We've created two very ugly stripes in the middle of our dubiously pretty color bar. And now we're going to use it. And so this I kind of threw in here last minute, but you can make subplots with this thing called subplot mosaic, which is a relatively new thing. It's built on top of grid spec. I have personally found grid spec to be hard to use and complicated, and I really like subplot mosaic. I see the question. I will talk about that later. It's probably the way your Jupyter notebook is generating. Sorry, I'm not supposed to be looking at chat. All right. So to do this subplot mosaic, we're going to do plt.figure. We're going to give it the constrained layout equals true. And then we're going to do dot subplot underscore mosaic. And inside of here, there's many ways to do this. I suggest you go look at the documentation, which is, I think, linked, might not be linked. You can Google it. And we do 3 and then 3. And then we define where we want the subplots as named things in the string. And so I'm going to want 2 subplots, one right here, and then another one under it. So 2 subplots on the top, 1 on the bottom that spans the whole range. And so to do that, I'm going to do 2 subplots on the top, and I need them to have different names. So I'm just going to call them A and B, and then enter. And then I want 1 subplot on the bottom, CC. They don't have to be called A, B, and C. You can call them actual things, like actual strings, like this one is the bar graph, this one is this thing. But for the point of this and being fast, I'm just going to call them A, B, and C. And so if we do that, will that show up if I just run that? Yeah, it will. So you can see we've created a dictionary here, which is the output to this. We're going to output it to something called ax dictionary. It's created a dictionary of the axes, which is roughly the same as the subplots here, except for we can't reference them by index. We reference them by A, B, and C. And this is how it looks, A, A, C. You can do it. This is so cool. I really like this. I wish I had more than 6 minutes. It's so cool. And I'm going to do the first one out, and then I'm going to copy and paste the next ones. So I'm going to call this histogram A, hist A, and then I get the axes instead of ax0, ax dict A, which is what I called up there. And then I do dot hist 2D. And all the inputs that I was giving hist 2D. And I'm going to copy and paste the bottom 2 for hist B and hist C. And so for color bars, what I want is I want a color bar that spans the top 2, and then I want the bottom one, plot C, to have its own color bar. And this will make more sense when I plot it, I promise. All right, so this is a really ugly plot. So for the first one, I've used Pretty Color Map, which is the one without the green and pink segments in it. For the second one, I've used the blended one, the blended rainbow one that we created above. And then for the third one, plot C, I've used the color bar that used the green and the pink slices through it, which you can see. And this is what I was talking about earlier. I've created a shared color bar for A and B, but it's not accurate to both of them. I've just spanned the color bar for A across A and B. Additionally, you can see I've chosen to put this location on the right. I have this one on the bottom. You can expand this to as many proportions as you want. This is the most I could think to do with color bars. And down at the bottom, we have a plot types cheat sheet, choosing color maps in matplotlib, which is the color maps theory that I talked about above, making custom color maps, which is, oh dear, which is where most of this came from, had to do this. and complex figure and subplot generation, which is where how to create things like this come from. I highly recommend it. It's super interesting. And anyway, that concludes our second matplotlib tutorial. Thank you for your time.
Thank you again, Anissa, and thank you everyone for attending. We just have one question in the chat that's still outstanding from Linlin.
I see that. I have never gotten that when I've run this before. I'm not totally sure what's going on. I think it, I think what's going on, instead of rendering in what I assume is Jupyter Notebook, maybe Binder, instead of rendering the output to be pretty, it's simply returning the matplotlib object. It's doing it correctly, I'm pretty sure. Except for whatever version of JupyterLab or whatever version you're running this on, just it's not just generating the color map. That's the only thing. It's perfectly fine. You just didn't get the pretty cool output.
Thank you. And thanks again. Everyone, please flood the chat with your gratitude. And everyone who's watching this virtually, I hope you found it useful. And we will see you again in another 2 weeks, I believe.